trees, right? We were looking at trees. Let me formally define trees today, okay? So we have trees. So I'm going to formally define it because now we are going to count the number of trees, okay? So let's first give the formal definition so that it's absolutely clear what we are dealing with, because we have seen it from different perspectives and it was a result of an optimization question and so on, but just let's see it formal definition. I'm just giving a definition. Okay, we have seen the motivation and everything. So a tree basically is a graph. Okay, a graph, and a graph, as you know, is just endpoints, and some of them are joined by lines and some of them are not. That's all. Okay, a graph which is connected. One second. Yeah, can everybody see the screen I'm writing? Okay. Is that, yeah? Okay, right. A graph which is connected, that's the number one condition. And this definition will be good for us and has no cycles. Okay. Does everybody agree that this is the definition which we are dealing with? Okay, is a tree. Okay, this is exactly what we had. Now, again, let's just quickly review what does connected mean. Connected here means that between any 2 points, there will be a path. Okay, using the lines that are there in the graph. We'll give some examples, but there will be a path. And there is no cycles. The intuition, or rather the real reason why we don't have any cycle, the intention behind it is that we want a graph which is connected but minimally connected, meaning that there is no extra lines. It's the optimal connected graph. Okay, but in any case, this is what it is. There is a certain interesting way to draw trees. Okay, I'll just say nice right now, because yeah, a nice way to draw trees, because trees come up in all sorts of places, from recurrence relations to analyzing algorithms which don't have anything to do with trees to start with. Okay, tree is just a kind of a structure, which is somewhat like, it's kind of modeling something where you can reach from any point to any other point in a unique way. Okay, so all sorts of things use trees, even recurrences, as I said, and so it's good to be able to represent it. They also use an order theory, which we'll see a little bit, pochets and all, which are used in Olympiads and theoretical computer science and so on. So a nice way to draw trees. Because you see, when we are going to count something, it's good to see how it can be drawn in a way that can help you to see how many choices you have at each step and so on, so that you can count. Okay, so nice way to draw trees. Let me first just draw a tree in a bad way, or just in a random way. Okay, so here is a random drawing. Okay, so I'm taking some points, and as you understand, in a graph we just have points, and we just are interested in which pair of points are joined to each other, so which pair of people are related. It doesn't matter whether that line is straight or curved and so on. So never get confused about those things at any stage. Okay, yeah, I mean, graphs can be described in more formal ways, but for us, just like this. So these are some points. So we have 2 to 4 to 6, 8 points. Just drawn them like this. And let's say they are just joined. It's a different color. Pen. Let's say they are joined in this way. So this is a tree. Is that right? This is a tree. Does everybody agree? Yes. Where is the cycle? That's right. So this is Yes, yes. Absolutely, absolutely. That's right. So this is not a tree. I know it's a very, very simple thing, but just to, just draw it for the first time for those seeing it. So this is not a tree. And the reason why this is not, well, already said there is a cycle. Now, formally, what is a cycle? Okay, a cycle is basically you start from a point and you move using the edges that you have. That's important. And you move and you keep moving and you come back to the point. It's a cycle. Now it may not look like a cycle in some, yes. No, you cannot call it an Eulerian trail. That's a different thing. That's a slightly different thing. So since you have brought it up, an Eulerian trail would be something that visits every edge of the graph. This particular thing doesn't visit every edge of the graph. The two edges are missing, right? But in some sense, you are right. You could extend it to make an Eulerian trail if you, for the time being, that's a very different topic. So let's not bring that. In any case, well, not very different, but in any case. So it's not a tree. And so you can remove, in fact, you can remove any of those edges on the cycle and it will become a tree. Okay, this is a tree. Okay, this is too simple. Maybe it's also a tree, but it's just a path. Let me remove this one. Everybody agrees it's a tree. There is no cycle, number one. So you have to check two things. No cycles, and the second is should be connected. So this is just, we are just trying to get hands-on experience with trees and such. That's all it is. There's nothing new I'm saying here. Okay. This is a random drawing of a tree. It's a connected thing and so on. It doesn't even look like a tree. Right? Here's the thing. How can you draw it in a more systematic way? It may look like a waste of time now, but it's a very useful thing to do. Okay. Obviously, you won't be usually doing this manually, but you should know the method that it's used so that you can do mathematical reasoning on that. You can do induction on trees and many other things on trees if you have that systematic thing. So we'll come to a systematic drawing. Now, since the question is vague, let me answer it myself. My point is just, I'm saying that we want a systematic drawing. Now I'll just say a systematic drawing because you see there are many ways to draw this systematically. So what's the first step in that systematic drawing? And it's very important to, really to draw it systematically, as I'm saying, and these see it moving forward later on. So the first step is that you fix one thing systematic, right? So we want to fix one thing as the root or as the chief ancestor, as the first ancestor, Adam and me, first one. So we just fix this one maybe. It doesn't matter, you could have chosen any one of them. Okay, but I'm going to choose a 3 because it looks pretty crowded there. So it will look good if we draw it. So we'll put this right on the top. So again, I'm not changing any information. I'm just changing the representation of the information. And a lot of mathematics is basically about just that. Okay, basically about that. So you see what I'm doing. This will be a very important practice. Do this like this. And then we'll just, 1 minute, draw lines from there. Obviously, just what we have to draw, we'll draw. So we'll just draw the neighbors of 3. Now neighbors, as you can understand, just those which have edges, 2, 3. Just that's what neighbors mean. We have 3, and we'll draw it like this. And what are they? We have 2, we have 4, and we have 8. I also put them in an ascending order. It's very simple, but and now maybe we can see what should be the next steps. Since I think now seems to be a way in which we are moving forward. Yes, that's right. Yeah. So you just take the neighbors of 2. There is only one neighbor. So you just draw it like this and draw it on the 3rd level. I'm sure you guys understand, right? third level. And similarly for 4, you draw its child. So this is called means a neighbors of 4 that is below 4. Okay, so below you can understand that really depends on where you start from. That will depend on different people will draw it in different ways, but this is a way to draw it. So it's a tree that is rooted at 3. 3 we are treating as the root. Well, it should be upside down, but just drawing it like this. So you can understand. And in the same way, with 8, now it's very easy. Just join the 7, and with 7 we'll join the 6. You see this. This is trees are a very important model, as I said, for all kinds of things, from web problems to recurrences to analyzing algorithms and all sorts of things. Okay. And direct questions also. This. And now we should label the points. So this is 1. Typically, 1 will be taken as the root usually, but it doesn't matter. It depends on 5, and this will be 7, this will be 6. So I've not done anything. It's same thing. It's same graph. It represents the same information, but it's much more systematic. Okay. So we say that 2 is the parent of 1. 2 is parent of 1. And this is just some simple terminology, very obvious terminology. And similarly, 8 is a parent of 7. And you see these things which do not have any parents, these are called leaves. And that's obvious. If you just imagine it upside down, then you see those will be the leaves, called leaves. These are important concepts, maybe concepts. Yeah. These are the leaves, and then these are so the leaves are those which are not parents of anything. The leaves will only have one neighbor. Is that clear? Every leaf will only have one neighbor, right? So if there is a so what is a leaf? A leaf, can anybody try to formally define what a leaf should be? So in this picture, I have said that a leaf is that vertex. That's a good definition. That's right. Yeah. So the way I was defining it was slightly informal, but that's really the way, that's the origin of it, was that it doesn't have any parent. Sorry, it's not the parent of anything. Okay. But if you want to define it if you want to define it in a way that is free of the way you've drawn it, okay, that doesn't depend on that, then it should be defined as the way someone said. A leaf is just something, a leaf is a vertex with degree 1. Okay. Degree just means the number of neighbors, degree 1. So those which are degree 1 vertices are leaves. These are absolutely important, because if you remove a leaf from a tree, then what you get is still a tree. Is that right? But if you remove a non-leaf, if you remove 8 from this tree, then it just breaks apart. It breaks apart into 2 disconnected graphs. But if you remove a leaf, or this, we say if you pluck a leaf, then the tree still remains a tree. Okay, these operations are very important. They'll come up in the problems, but right now I'm just saying this because we'll be using these words in things, terminology, and counting the number of trees. Okay. So far so good, right? So we have an understanding of what a tree is from this perspective, from a more mathematical, less algorithmic perspective right now. Okay. Obviously, we have seen the other versions of things, other versions of trees. So these are the ways to draw trees. So let me remove these now and come back to the things. You see, we had defined trees in other ways, which will not be very useful for us now, but we know that, okay, this one will be useful, that graph with n vertices and n minus 1 edges and connected. This can also be taken as a definition of tree. See, we have proved that these are the same things, right? These are the same things. Basically, the idea is that the minimum number of edges needed to make an n vertex graph connected. And yeah, and the other way is that connect n minus 1 edges n vertices and no cycles. That's another definition, and we can go on, but we don't need this one. You'll probably just need it. So these are the varied definition. Now the question for today that we want to really answer first, before moving to that algorithm, is about finding the minimum tree, the minimum weight. Is there is the question, how many trees? And maybe I should say that this is how many trees on n vertices. And this is a question that I think a lot of you would have already asked yourselves or already tried to find out. Right? This is, or maybe you already have found out. Okay. This is a very natural question to ask, right? Especially because we had seen the following theme. And this is just tying back to the previous thing, the theme. You see, the theme was that I'll not write words, we know that there are many trees. And once again, that was because every maximal construction that you do, so that, so every maximal connected or every maximal graph with no cycles, that was really how we had got the trees, right? Because algorithmically, we had seen that any maximal graph with no cycles, meaning that you just try to add edges at each step so that you don't get cycles. And that's it. That will give you a tree. And you can do it in so many ways. It was already clear, right? So we know that there will be many, many trees. And I had also mentioned that whenever you have this kind of solutions where you just apply a greedy algorithm, then the answer will usually be exponential. There will be many, many trees. There will be many, many of those optimals. Okay, this generalizes to finding number of matroids, something in theory. But for now, we'll just count the trees. Okay. So number of trees on n vertices, and the intuition is that there are many, many trees. We had seen this in various ways, this theme, this principle. And today we will quantify this principle. That is really what we want to do. So how do we answer this question? Okay. So I think we won't need the definitions now, rather we'll need pictures. Okay. So we are going to first try to find a pattern. I think that is thing, you take small numbers and you try to count. Okay. So let's take, so here let us record things. Okay, and this is again a general way to approach questions, right? About counting, you try to see a pattern if you don't know how to, really. It's obviously this is an obvious method. We take n, so let's start with n equal to 3. You can start with n equal to 2, but let's start with n equal to 3. Okay. And there is also, we will also see some interesting points here. N equal to 3. So n equal to 3 means my vertex, let's introduce more things. My vertex set is 1, 2. Okay. Yeah. So what are the trees that we can draw on 3 vertices? Or rather, I should say the vertices 1, 2, and 3. What is the first tree? Just a path, right? Just doing it like this, just to make this not a line. It's just this is this is this. I should also label them, right? 1, 2, 3. Okay, so this is 1. What are the others? Yeah, let's go ahead and say. Repeat one edge, meaning? Yes, obviously. Yeah. So they are different trees, right? You can obviously, yeah. The whole tree should not be the same. Yeah. So you are referring to another question where we were, no, but here, we can. That's right. Yeah. So you see with this, so this is the important point. With this shape or with this path, you can get many trees, right? I'm not going to draw all of them, but you see with this particular shape, you can get many trees. Yeah. How many will you get? Oh, hold on. Am I making a mistake? No, no, yeah. So let's just draw it. We'll see. So there's this one, and then there is another one. Just tell me if there 3 factorial, right? You're saying. But let's see. That's the, if you count it naively, that it seems like 3 factorial, but let me draw and then you guys can tell me. Okay. So actually through this, we will actually understand more about what does it mean for 2 graphs to be same, and what does so on, so on. Let's try to understand that. So if you're saying 3 factorial, then let me just draw one more, this one. Okay. And then if I go ahead, before I go ahead, are these 3 okay? Or is there some problem? Are these 3, just think, let's think about this again. Are these 3 good, or is there any issue? Absolutely, they are the same. These 2 are the same, because you see in a tree, as I repeat, as we know, the definition says that all we care about, all the definition of a tree only cares about what is joined to what is related to what. And you can see in this 2, there is absolutely no, I'm not saying if you rename and blah, blah, then you will become same. No, they are absolutely the same. With no change whatsoever, they are the same. But they're drawn in a different way, but then you can draw it in infinitely many ways, right? These 2 are the same. Let's make it very clear. And so this is basically what this is. The collection of edges here is 1, 2. This is one edge, 1, 3. And then here also it is the same. So these are the small things that we really understand from this theoretical discussion today. Okay, usually we'll do more problems, but just trying to learn the language and be clear about things. You see, these 2 are the same trees. There's absolutely no difference. Okay, so they are same. So then it will not be 3 factorial, and that's the reason why counting trees becomes complicated. Okay, so that's the reason why, that's one of the reasons why it becomes complicated, because at some levels the order doesn't matter, in some cases it matters, and it just gets very complicated. So then what is is there any other tree? Absolutely. So that's the thing. So what is in the middle, that really matters, right? That will really give you a different tree. Well, different in some sense and same in some other sense, but for us they are different. And they are same in some other sense. You can already kind of feel it, right? These are these are more or less the same. So these are what is known as isomorphic. I'll not define that. We will define it later on, and also we'll deal with the technique to count it. And that technique, we will try to learn some interesting algebra to do that technique as a apply that. And that's also used in, but we'll see that later. Right. So what is in the middle really will give you a different tree. That's very clear. Right. This here different, because in this one 2 has 2 neighbors, this in this one 1 has 2 neighbors, and in this one, oh wait, 3 in the middle, right? Sorry. Sorry. Yeah. Okay. So these are 3 different trees, and obviously there is no other tree. So the answer in this case is 3. Okay. So for n equal to 3, let's just use t of n. So it's like taking the input n and number of vertices, and it's giving number of trees. It's 3. Typically, it will be not drawn like this. It will be drawn like this. That's how I should have drawn. But anyways, doesn't matter. So really, we don't see much because this is such a small case. Let's go to 4. And we'll try to draw it in that way, where you had a root at the top and then from top to bottom. Yeah, so how do we get started with 4? So now maybe change. That's right. Yeah. So the path. So you have 1, 2, 3, 4, and here you have. Okay, let's. In this case, it. Uh-huh. Yes, that is also a way to do, but sticking with the way we are trying to do from top to bottom, we'll just do it like this. Yeah, that's another way to do it. Certainly, that's maybe can the same thing. Yeah. So this is what you have, and here you have 1, 2, 3, 4. Now let me ask a question. With this particular shape, so what do I mean by this particular shape? That's the loose term. But this with this particular shape, and remember what we're trying to do is in that in all the trees we are counting, we're trying to fix one at the top to just lessen the confusion, just to make it more systematic. We're trying to put one at the top, whatever the top means, top. How many trees will be there with this particular shape? Yeah, 3 or 6. There is a question. So I think there will be 6, right? Because you see, it really matters. The order here will really matter. Really give it. That's right. And they will give you different trees. No, we have to still be careful. 3 ways, 2 ways, we have to be careful because here it didn't work, right? But in this case, you see, it gives you different. Because you see, what you put here will be counted as the child of 1. And what you put here will not be the child of 1. So you can just reason yourself in that way, right? So it will really matter. The order will really matter. Just to concretely this, and just will not write all of them. So just roughly drawing it. This, you see, these two are obviously different because here 1 and 3 are joined and here 1 and 2 are joined. So you see the order really matters here. So in this case, it will be 3 factorial or 3 into 2, 3 choices, 2 choices. You can just do this. So there will be 6 trees. So this, you see, this counting process of trees is interesting. And it's a very rich, I mean, you can discover linear algebra and all sorts of interesting maths through this problem questions like these. So it really goes very far. Okay. So there are 6 of this type. 6 of this, just let's say this type. And all these 6 are similar, right? And later on, we'll see that all these 6 are isomorphic. Okay. Where in isomorphic, basically, we are loosening our sense of equality, right? And then a lot of things which are different, but they are in essence the same, become the same. Okay. But in any case, let's not get into that. No, this is 6 trees of this type. Now let's go in. So you see, my point here is that to do this kind of problem, even if you do not have a formula, and this is very important because you can't know all the formulas in the world, right? For an exam and so on, or whatever you're doing. The idea is that I mean, this is something that naturally do. So really, maybe it's not very helpful what I'm going to say, but the idea is that you break it into the types. What are the different blueprints? What are the different types? What are the different shapes? And then you fill them. So this is like a smart way to do casework. Okay, that's what we're basically doing till now, right? So yeah, so what is the other shape? What is the other type? So what is the other type? Type 2. You see, in this case, we had 1 and 1 had only one child. Okay, in this case. In the next case, we can just change that and we can just say that let 1 have 2 children. This is a different shape. And then one of those children, one of those is not a leaf. So we can say this is a new shape. And now all we need to understand is how many ways are there to fill this shape. Okay, so this is a new shape. And obviously, see, this shape and this shape are the same. These two are no different. What is related to what is going to what can be seen from here can be seen from here also by some filling. So those are really the same. So this is really a new shape. And now the question is, how many ways are there to fill this shape? So yeah, just take your time, think about it, and then we can just write it out. Obviously, you see, I'm going to put 1 on the top. according to the convention. So that is just for just the advantage of what we have seen now, systematically drawing it and so on. So how many of this type? 12. Okay, let's wait if some other answer is coming. I think 12 is a lot. 12 is a lot. It's not 12. Because you see, you only have 3 things, right? Yes, it is 6. Just check that it is 6. Because once again, you see, all you need to decide is what you're going to put here and what you're going to put here. And those are going to matter. The order is going to matter. You can draw it. Please, if you want to be more comfortable, if you feel like you need to be more comfortable with this, just draw all of them. That's the way I did it when I was doing it. I still do these things. When I do it, I just draw it sometimes just to clear and then just sit back and look. Yeah, that's all. That's the same thing. But yeah, but I would like to fill this level first. But in any case, yeah, that's another way to do it. It's the same thing. Basically, the point is you have 3 choices here and 2 choices here. Let's draw a few of them just to make it clear. So you have 2, 3, and 4. And then you have 1. And just to show the point, these two are different. These two are different here because 3 is joined to 4 here and here 3 is not joined to 4 in this. So they're different, not equal. And then similarly, you see, so you see just different choices here. You can put 4 here and then you can put 3 here. Well, let me say you put 4 here and 2 here, and then you're forced to put 3, and they're different. And in this way, you see, you can go on. Please do it. Do it yourself. If you do it yourself, just write all of them and see all the 16. Okay, we'll see that they have 16. We'll see all of them. Yeah. Let's go to the, let's see if there are, maybe it's not 16. So let's just check it. 6 of type 2. Are there any other shapes? Is there any other shape we are missing? Shapes, you see, knowing the shapes is very important. And this is the same method is used to also count chemical compounds, enumeration of chemical compounds also. But that's a little more complicated because usually I mean, yeah, that's there. We'll see that a little later. Not now, much later. To another 2. That's right. Yeah. So if one has only one child, okay, and then that has 2, that's the other shape, right? Exactly. Yes. So that's the other one, right? So yeah, you see, in this way, you will not miss. You see, if you do it based on the cases, then you will not miss it. So this is really a very easy thing and also far reaching at the same time. So this is the other shape. And just please quickly try to tell me how many will be there of this type and so on. That is right. The last one, only one will be there. So that's an important thing. Okay. Yeah, these are the things that gets clarified. There is only one of this type, one of type, let's call it type 4. Isomers, I actually don't remember. Yeah, something like that. No, not isomers. I was just saying just organic compounds. And under isomorphism and isomers are slightly different. Okay, I think mathematically I know what they mean. Chemistry, I don't remember. In any case, this one will be what? How many of this type? So all you need to do is choose this one, 3. Yeah. All you need to do is know what you're going to put here in the middle. The other 2 will be decided and their order doesn't matter. So this will be 3. please, if anyone has doubts, clarify it. Okay, it's very important to, and not just to understand what is same, what is not same, and these things. Okay, so that there's no misconceptions you end up having. So 2, and in this way you can, yeah, 3 will be the step. So what's the total? The total is 16. Right. So is there, you see, it was quite fast. We did it quite fast, right? If, I mean, we were explaining, going back and forth, but it's still, you see, if you just do it, you can very quickly actually also find n equal to 5. So please try to do this. Okay. You will find out that it is, and I'm just saying it because we didn't move forward, but please do it yourself. Please, like, try it and you will get, it's 125. And it seems very big, but it would not be, because see, we counted these 25 in just 4 cases. Okay, sorry, 16 in these 4 cases, and it will grow very fast. So unmistakably there is a pattern. Okay, so yeah, so what should be the, okay, right, that's right. Does everybody agree with that? Yeah, on n, if you have n, no, yeah, that doesn't, yeah, maybe, I think that's right. But you see, even if n is equal to 2, it's correct, right? If it matches, right? Because if n is equal to 2, then it just becomes 2 to the power 0, which is 1, and that's right. Because, so no, you can, it works with small. Yeah, not for 1, it doesn't work, but those are trivial cases. But for 2, it does work. So this is a connected graph, right? This is connected, because any 2 points, if there are no points and no 2 points, then it's automatically connected. That's true, because you can prove it's not false. Okay. So in any case, oh yeah, so then also it works. And yeah, I don't know how profound those things are. I mean, but in any case, these things, what is what we get. And so the claim is that we get this. Okay, but the question is, how do we prove this? This is really the question. So far, we have just tried to gain intuition. So this will be the counting question that we are interested in. How do you show that there are so many n to the power n minus 2 trees? Recurrence, yes, you can try with recurrences, but recurrences is usually very complicated for this. Okay, because you can understand, it's not a linear thing, it's a branching thing. It keeps branching and you can try induction, but the reason why induction, so there are 2 suggestions, and all of them will work some way or the other. Okay, but it's difficult to make them work. Recurrence will be difficult, obviously, because you see, why is recurrence difficult? Because if you have a tree on n vertices, then the way you can go to trees, well, recurrence and induction are quite similar in some sense, right? If you want to connect it with trees with n minus 1 vertices, then, well, you can remove a leaf and you get a tree with n minus 1 vertices, but those are not the only ways. There are some fundamentally different trees with n minus 1 vertices. So it gets complicated. Okay. And also, you see, another thing that should tell you that it's a big no-no for recurrences and induction is that, you see, this doesn't have a good, like, you see, if you call this thing, if you call this the nth term of something, and then if you take the n plus, just imagine, right? And if you then take, this will be the n plus 1th, yeah, answer. How do you connect these two things? They're not connected in a good way, right? You see, how do you connect n plus 1 and an? Not very obvious. How do you connect them? There's no clean relation. Even if you take an minus 1, then those 3 terms is not well connected. So it's not easy to build from the small cases, right? If you say, no, I'll expand this, you expand this, you'll get something very complicated. You'll have binomial coefficients, all sorts of things. So no, recurrence and induction, well, it does work. There are ways, some very heavy machinery used. But I think they are not the kinds of proofs we are right now interested in, but they have their own merits. They are much powerful. They are used in other places, like counting the number of isomorphic trees. So that's a much more harder question, is how many shapes are there. So you see, counting the total number of trees has a very clean formula, right? But if you ask how many different shapes are there, this shape is 4 shapes in this case, right? And the number of shapes, that doesn't have a good answer. I think that there is no answer for that. There's no clean formula for that yet. Nobody knows in the world. I think there are some complicated formulas, but no closed formula. That is usually hard. You see, for example, some of you have done, if you take a number and you try to ask the number of partitions of the number n, right? If you ask for ordered partitions, then there is a formula for that. We'll see that in the counting class maybe, and also some of you have seen it. But if you ask for actual partitions, means partitions in which you consider this partition to be the same as this partition, let's say the n is 6, it is to you consider same and so on. That's right. Yeah, partition of a number. If you take actual partitions, then counting the number of partitions is impossible. There is no closed formula. But if you take ordered partitions, meaning if you consider these two as different, then there is a formula. So always, if you go to the actual, if you ask for the number of shapes or the number of partitions and a number of things in which you kind of say that order doesn't matter, then it usually becomes complicated. And the same thing happens in even binomial coefficients are slightly more complicated than in factorial and so on. Okay. In any case, so those things will work. We'll probably see them much later. But right now, how do we get this? Let's think about what else counts n to the power. What other counting problem would have n to the power n minus 2 as an answer? Okay, so think of a counting problem, a simple one, because counting problem with answer. What's the simplest, I should just ask, counting problem that gives you n to the power n minus 2 as an answer? And obviously you have this n things. How do you get such a thing? Just think based on the choices and such. What kind of counting problem will give you this as an answer? So I'll just remove this. Draw more complicated trees. So what would be the easiest one? You see, if you have n to the power n minus 2 as an answer, what does it mean? It means two things, obviously, right? That at each step, I should just say, it means that you had n choices. That's right, yeah. N choices at each step, and you had n minus 2 steps. Some problem like this, right? Where you had n choices at each step, and you had, and the most obvious problem is that you just take yeah, yes, we will eventually show a bijection. That's right. That is what we're going to do. Okay, we are going to show bijection with a simple problem whose answer we obviously know is n to the power n minus 2. Okay, and well, the most obvious question problem is this. So find the number of n minus 2 tuples. Tuples here just means, it's just order tuples. Okay. N minus 2 order tuples. Okay. With inputs from this, from this set 1 to n. Okay, this just means, I'm sure you guys know, but it just means that you could have something like 1 1 2, you could have n 1 n minus 1 and so on. Okay, so n minus 2, this is 3, but it's in where we will have n minus 2. So example, very simple, but just writing it. One is this. This is one particular order tuple, right? It's a Cartesian product of n two things. Okay. And then in this way, you see you could have n minus 2 in all of them. So basically all possibilities, just all possibilities. Okay. You could also frame this in terms of functions and such. This is the simplest formula. There's no simpler formula than this. So this is the simplest rather problem whose answer is n to the power n minus 2. Because see, for each place, for each coordinate, you can call it, you have n choices. Sorry, you have you have n choices. And then n minus 2 of them. So n times n times n times n, just independent n to the power n minus 2. Okay. Sorry, I didn't get. Why do you have n minus 2 choices at each step? No, but at each step you have n choices. This is an example. This is another example. Is this clear with everyone? The number of n minus 2 ordered tuples, the tuples with n minus 2 coordinates. Simply just n minus 2 places which you want to fill with these n numbers, you can repeat the numbers. Okay. That's all it is. Just a list. You shouldn't even call it out, just a list. Find the number of n minus 2 sized list. N minus 2 sized or length lists. Just a list with inputs coming from 1 to n. So obviously this is n to the power n minus 2. So what we want to show is that the number of trees is also the same. Okay. So what we will do is we will take a tree. Okay. We will take a tree. We'll take some examples right now. And from a tree, we are going to very cleverly, obviously it's not my method. We are going to very cleverly, but we see the principle. Okay. We're going to very cleverly associate a n minus 2, so from a tree to a n minus 2 sized or length list with inputs from 1 to n. We will do this for every tree. So I'll take a tree and I'll show a recipe, a method to create an algorithm rather, because you can write it in simple steps, each step being very primitive, but then in the end it gives a very, very beautiful, powerful result. N minus 2 sized list. That's the first step we will do, and then later on we'll see the other way. Okay. Let's first get started with this. See how we should move, how we want to go about doing this. Okay. So this is an idea of encoding. You have a process, but you want to encode it, and it really goes a long way. Okay, you have binary sequences and kinds of binary sequences, and these accounting problems appear in all sorts of exams and such. And in general, this is very important. So let's see how to take a tree and get a list. Okay. So what we'll try to do is from a tree to a list. Okay. Let's just take an example. That's a best way to understand. So this is a really ingenious method. Okay, so so we'll just draw the tree nicely in this layered way, so that, and you see, this will be very important to execute this. thing. If you draw it in a random way, then it might become confusing. Okay, so we will draw a nice tree. Yes, I don't want to give the impression that all have the same height. Yeah. So this tree is here. See, so they have different heights. See, this chain has a different height. This is a different height, and so it could be. So what is n in this case? So simply we can number it like this. Yeah, but let me not number it like this. This might give the impression, it might give a very specific kind of list. So just let's number it interesting way. 7, 6, 3, 4. So this is a tree, right? We have drawn it in this way. It will help us to execute the algorithm. Now, how is it that you will go to a list from here? What is the procedure? Okay, what kind of ordering? Yeah, some kind of ordering. Let's think about it. Let's think about it. So you have n equal to 7. So we want a list here of length 5. Remember, you want a list of length 5 here, not 7. Yeah. It is kind of an ordering, but it's a bit more complicated than that. Longest chain. If you just, you want to, so remember that we want to make the list in a way that later on we should be able to go back. That is really the essence, right? That will be the magic. In some sense, right? We want to make the list in such a way that we use that the entire tree is in the list. In some sense, this entire complicated thing, second order kind of data, right? It's because it's like you have subsets 2, 3, 5. Well, but yeah, it's a very complicated thing. But we want to put everything in the tree, everything that is in the tree in the list. We want to put all that information. That's what's known as an encoding. Okay. Yes, at least in a simple sense, that's what it means. Okay. So the idea is that we want to put all the information in that. So if you just take the longest thing, those kind of things are not going to work. Okay. Ordering seems an interesting thing, but that's, I have to say something, it's a little complicated, ordering of trees and such. But also ordering, if I order a tree, I have to think about that. Do we get a no, no. So the answer is no. For I'm sure we don't know. Most of us don't know what ordering on these things mean, but and also maybe formally, yeah, it's difficult. But ordering also will not work. So I will show orders later because we'll study partial ordered sets which are partially ordered. Some, and those are very important in solving again. We'll basically see it in the analysis class also on Monday. This will be just important to get started with, increasing sequence and so on. Okay, orderings, partial orderings. Okay. But no, because the idea is that if you know what ordering a tree means, then then from one order you can, from one particular order you can get many trees. So that will not work, unfortunately. So that will not work. Yeah, from a particular ordering you can get many trees. Because I mean, in sense, I think all of you guys can understand there is some sense of ordering is also there already there in the tree, right? Because there is a parent-child relation kind of thing. So there is some sense of ordering has already come in. Okay, but 5, 2, and 5 are not ordered. So that's what goes into the theory of partial order. But we will not go into theory first. We'll go through problems. So we'll see that later on. In any case, let's come back to this question. How do we create a list that contains everything? Okay. So you see, we talked about leaves and such, right? in some sense, the idea is recursive. Okay, but it's a very ingenious recurrence. Recursive meaning that we will make smaller trees. Okay. So how do you make smaller trees? So let's write step here. So step one is how should I say? So, yes. Step one is remove. I'll just use the word remove or pluck. Remove the smallest numbered, I should say, smallest numbered leaf. So which one is there in our, what's the smallest numbered leaf? Right? 3 is the smallest numbered leaf. So the leaves are 3, 4, 5, and 6. 5 is also a leaf. Okay. Degree 1 doesn't have any child. But the smallest one is 3. We want to say smallest so that the uniqueness is there, right? So that we can recover things back. That's why we're putting this in smallest. Remove the smallest numbered leaf and record the number or the label. Label is the right word, but I'm just using number of its not of the leaf. So we're not going to record the number of the leaf. Record the number of its parent. Well, only one parent, right? Every leaf only has one ancestor, one immediate, well, I should not use the word ancestor, one immediate parent, because its degree is 1. Or just use the word neighbor is also good, but parent kind of is more telling. We're recording the number of its parent. Okay. All these things make sense. If you just record the number of the leaf, then you're just going to get a list. See, just think about it, right? I mean, so I'm saying that there are only very few things to remember at all, if at all, in this thing. If you don't put the word smallest, if you're just doing this, investigating this problem, we don't have much time, so we're just going here. But try to just reproduce this yourself, and when you get stuck, just use the reasonings yourself. We are using smallest so that we can recover the things back, so that there is a unique way, well-defined way in which you go forward so that you can come back. There's one unique way to come back, right? That's the why smallest is important. Or you can also just do it with the largest. It really won't matter. I think it will not matter. Yeah, but smallest is just for convenience, but it's should be a proper way to say it so that you can come back. And recording the number of its parent. Can anybody tell me what would happen if you just record? Because the obvious thing is to record it's the leaf number. What happens if I just record the leaf number, then I get 3, and then maybe I remove this? That's the most obvious thing to do, right? Once you have recorded it. Then what's the smallest thing? Then there is 4. So you remove this. Then what's the smallest? If you do this, then what will be a problem? Maybe someone can tell me. After this, obviously, I'll put 2, because 2 is now a leaf. Once you remove these things, 2 becomes a leaf, right? See, this is gone. So 2 becomes a leaf. We put 2. Then you can remove 2. And then what's the smallest? The 5. And then you put 6 and so on, right? You go on like this. Maybe 7, or maybe 1 and then 7. That's right. That's right. Yeah, 5 and then 1, right? Yeah. And then we already have the list of 5. What is the problem with such a list? What's the problem with this? What's an obvious problem with this method? Suppose you long time after you forget and so on, you just do this. What is obviously doomed here? Not going to work. How can you obviously say that? Oh, that is okay. They don't appear in this, so they won't appear in this tree. It's fine. I don't need to use all the things in my list. I just need a list of length 5. So 7 and 6 may come in from some other tree where 7 and 6 maybe are the leaves. Mhm. This may not be unique. So that is what you are claiming, right? That's right. Maybe no, but let's see. So let's see if you're saying that, let's see, can we get a tree from here? Okay, you can because you already have. Can you get a unique tree? So maybe let me change the list. So basically, we want to see if you can go in the reverse way by this method. If you just follow this method and not the method that I was just, if you follow this method, then the question really comes, can you uniquely go from this to a tree? Let's change the list so that we can honestly do it. Let's say if I just put 1, 2, 3, 4, 5. Can you make a tree from here in a unique way? So it means that one, right? One is a, yeah. Next to it, that's where, so I could also say that you can put 2 as a parent. That's why you see you can do this or you can do this. Both are going to, you can extend from both these constructions, right? Because this is also valid because maybe the only child of 2 was 1. And so if you remove the 1, then then 2 becomes a leaf. And so I mark 2 and so on. This also both work. So it's not unique, as Sham said. It's not, this method doesn't work. So always it should be unique because we want to show a bijection, and we want to show an exact bijection because we know that for trees, the answer should be n to the power n-2. We have actually seen that. You can check, check for n equal to 5, draw the shapes and do it. And then we also know that this list things also count the same thing. So that's what it is about, right? So we know another thing, another reason why it is doomed is that, I mean, this list will only have unique elements. Obviously, that's another problem, right? This list will only have unique elements. And that's another problem. If your list only has unique elements, then you're going to get how many? You're not going to get a lot of, you're not going to get n to the power n-2 list, right? You're not even, it's not even a surjective map in the sense that not all the lists will come in this way. So that's obviously another reason why it's doomed, and so on. So it's doesn't work. This method doesn't work. So you see, you can at least know what does not work on your own. That's what I'm trying to say. And that's how you narrow and zone into the right method. It's very important to basically know this parent, this, knowing this at each level will give you the answer is the thing. But just, I'll just execute this in the reverse direction and so on. But later on, you have to do this, execute this many more times, and then get a feel for why this works and this thing. That's those things you have to just do. Okay. But in any case, length 5 list. So if you follow this method, then how does my list evolve? Let's do it. Yeah. So what should be the first item in my list if I follow this method? No, not the whole list. Relax. We just want the first one. Yeah. So let's just take the first thing, and this is 3. Yeah. No. So let's see. Let's see. So 3 is the first thing. Yeah. And then the step 2 is, let's make it clear. Step 2 is really nothing different. The step 2 is basically the obvious thing. Remove, we have removed it, right? So remove the leaf and number it. Repeat step 1. That's all. Okay, repeat step 1 on the smaller tree. So I should have first removed this thing. So maybe the way to do is to just black it. Okay. And yeah, kind of just removing it. So it was there, now it's not there. Okay, now in this tree, you need to look at the smallest numbered leaf. Okay, so by the way, this is already wrong. This should be 2, not 3. It's 2 because again, the point was that we want to record the number of its parent, not the number of the leaf. That was the mistake. Okay. Now, let's ask ourselves, in this tree, what is the smallest numbered leaf? That 4. And its parent is 2. So once again, it's just 2. And yeah, we are doing it very slowly, but just trying to understand this. And then, because if you do this very carefully, then the reverse will be much easier. The reverse is actually harder if you don't do this carefully. Okay. So what's next? That's right. Now that is the smallest, that node, that vertex is the smallest numbered leaf. Now no more is 5 the smallest numbered leaf. That's important, right? So 2 is the smallest numbered leaf and its parent is 1. So we will record that and we will remove this. Yeah, and now it's obvious how to proceed. The next is 5. Right? 5 is the smallest, so we will remove it, remove the edge, and we'll record the number of its parent. That's important. Okay. The next is 6, right? 6 is now the smallest, so we remove it. Okay, and we'll record the number of its parent. Uh-oh. Yeah, that's why I always make this mistake. Yeah, let's go back. Yeah, that is, you're right. I think that's, yeah. So till now we have this. Yeah, but that's right. So I've made this mistake. I'm twice, I think, today. Right. At this point, it's very important to understand. It's easy, but just that 1 is now a leaf. Yeah, 1 is a leaf. See, 1 becomes a leaf. By mistake, I was going to write 6. You would get the same answer, but that's not the point. Okay. The 1 is become a leaf, so you remove it. Record its parent, that is 7. Hold on. Wait. So we 1 minute. Yeah, there will be 2 1s already, right? Yeah, 2 1s are there already, and then now there is 7. 2 1s were there. I removed an extra one. And then you stop because now you already have a list of length 5. Because you see, you can already understand the 7 and the 6 now have to be connected. Okay, so that was that's obvious. So yeah, in any case, we have to stop here because we've got a list of length 5. This is the method. Okay, this is the method. So I think that it's very clear, right? So right now, what we want to show is that this association is what is formally called a bijection. It's injective and surjective. Okay, what we want to basically show is that for 2 different trees, you get 2 different lists, and for every list there is a tree. Those are the 2 things you want to show, right? You want to show that for every list there is a tree, and for every tree there is a unique list. There is a pairing. Then only can you conclude that both the sets have the same size. This all the trees on one side and all the lists on the other side have the same size, right? For that, you have to show that this is not enough. This is not enough because it's just shown that for every tree there is a list. What if for some other tree also you get the same list? Right? So this is what we want to show. Just not using the word bijection here, no, but the essence is, yeah, we want to show that we'll condense matters soon, but for the time being, yeah, I want to show that 2 different trees give 2 different lists. Okay, and all lists can be obtained. This looks quite a tall task, right? If you think about it, how do you show that 2 different trees? They have to take 2 abstract trees, and then if you show that they give this different leaves, they give different things. That one can reason it directly. Okay, and then maybe you can take a list and you can make a tree also. so that from the tree you get the same list back. And so you can show that all lists are obtained. But rather a more straightforward way to show these things is that we will simply take a list. So what we will show is we'll not show it in this complicated way. We will show the same thing, but a rather fundamentally new idea, and that is a bijection. That is showing that you can go in the reverse. Okay. So what we will do is that we'll take a list and we'll make a tree out of it. Okay. So this is a process from tree to list, and then we'll take a list and make a tree out of it in a way that if you apply this process, you get the same list back. Okay. So from this, so let's write what we're going to do now. We will show that you can take a list. I mean, see, it's very important that I say that the aspect that is that now, so this is a process 1, okay, where you go from the tree to the list. Next, we want to take a process 2 where you go from a list to a tree. But it is not enough to just show that there are these 2 processes. Can anybody point out why just showing that these 2 processes are there is not enough? If I develop a method where, or just just like this, to go from a list to a tree, that will not be enough. That's a slight miss. People is the incomplete part that's usually left out. This is not enough because you see what we want to show is that the way you go from a particular list to a particular tree, if you apply the first process on this, then you should get the same list back. Then only it's a true matching on the both sides between the trees and the lists. Otherwise, it's not. Otherwise, it's incomplete. Otherwise, there's still room for, 2 different trees could give 2 different lists. Sorry, 2 different trees could give you the same list. It's maybe it's possible, right? We don't really know. Right. So these 2 processes have to be reverse of each other. Okay, that is an important point. Okay. Right. And let's just see through an example. Okay, let's just see through an example. Let us, and some of you will obviously remember the tree also, but let us make a tree from make the tree from here. Let us use a method. Oh no, let's not do it. I think there's no fun in that because you all obviously know the thing, right? So let me just make a new list, okay, and just go from the list to the tree. And that will be so that I can think honestly, I think good. So we have the list. So we could, and again, I mean, we'll just keep the same n equal to 7, and we'll take a list. Let's just take a list which is this very simple list. Okay. Yeah. What kind of tree can you make from here? So we want to make a tree from here, from this list, which is like a reverse. We want to make a tree such that the list of that tree is this, right? You want to make a tree. So absolutely, that's right. Raghav, what were you saying? That is, yes. So yeah, okay. So this is what you have, right? You have that from 1 is the parent and 1 is the only parent. That's all it is. It's very simple. And so you see, since we have analyzed that thing carefully, now this is very simple, right? We know that this should be the tree. And obviously, if you apply this method of finding the list, you see that you will get the list 1, 1, 1, 1. This is what I was talking about, that how we want our technique to be such that this going from the list to the tree, and you apply that old process of going from the tree to the list, P1 process, or yeah, P1 maybe, then you get the same thing. Okay, then only it's true matching. But we want to understand what happens in general. Yeah. So let's try to understand that. Let's say if you have 2, 3, 1, 5, 5. What will be the tree? What tree are you going to get from here? What tree should you get from here so that when you make a list of that tree, you get this list? Let's think about it. Okay. What tree would have, just think like this, what tree would have given me this list? Right? Okay, that's right. So let's write that in words, I think. Yeah. So this 2 suggests that 2 was the parent. So in my tree, 2 was the parent of something. Yeah. Does everybody agree with this very small observation? Yeah. The 2 there, I mean, if I put, I mean, so there was some tree, I do not know what the tree is. Okay. But in that tree, when I was trying to make a list out of that tree, I put a 2 first, right? Which means that 2 was the parent of something. 2 was the parent of what? That is the question. What is this something? We need to know that. Yeah. Because I had my tree and 2 was here, was the parent. Yeah, I should have just drawn that. Yeah, but yeah, exactly. So that is the least numbered leaf. What is that least numbered leaf? No, but one, no. You have to think about it. Least numbered leaf. One is not a leaf, one is already a parent because one was a parent of something at some point. What is, how do you? And 3, right? It has to be the least thing that is not in the list. That is what it is, yeah? Because you see the leaves. So I should have maybe done it more in a way, but I think this is more fun if I write out all the properties and so on. Point is that look, in your process, when you're going from a tree, when we were going from a tree to this list, right? In that process, if something was a leaf, then it never appeared in the list. Leaves never appear in the list. That's very clear, right? At every stage in the list, we were only filling the parents. And also, every parent, everything that is a parent of something does come in the list at some point. Yeah. Okay. But the point is that the leaf is what does not come, right? So we need to just take the leaf, right? Because we need to take a leaf here, and that is something which is not in this list, and it is the smallest. Okay. Least number not in the list. And that's 4. Sorry, it's list. Okay. So this will be 4 here. Is everybody okay with this? Yeah. Okay. All right. So 2 is a parent, and then there's this. Now, what would you do if you are applying the, think about, just think I'm constructing a list from an imaginary tree, which I'm trying to make. Okay. But just assume the tree was there. Okay. So if the tree was there, then I put the 2, then I would have, what would I have done? I would have plucked this 4. I would have plucked the 4. I would have removed the 4. Well, at this stage, 2 might become a leaf. I'm not saying it has to. It may have become a leaf. I do not know. But let's go to the second number. The second number is 3. I put a 3 in my list. Okay. Why did I put a 3 in the list? Let's think about that. No, 3 is not a leaf. 3 is a parent. So 3 is a, so I'm putting 3 here in the list means that 3 is a parent of something once again, right? So I don't know, 3 will be, I don't know where it will be, it doesn't matter. Put 3 here. 3 is a parent of something. 3 is a parent of what? That is the question. No, it can't be 1. It can't be 1, right? Because 1 is still, second least element. That is second least. No, but the thing is that, look, now the tree has changed. You have removed the 4 from the tree, right? You have removed, so this is a slightly complicated point, okay? But it's simple. If you remove the 4 from the tree, okay, and if you look at your list, then you see after 2 becomes a parent of 4, 2 is no more a parent of anything else. 2 is no more a parent of anything else, right? 2 is now a leaf. 2 doesn't appear. That's right. That is right. Okay. That is absolutely the point. 3 is the parent of 2 because now 2 doesn't appear again in the list. So 2 is a leaf now. If it was not, then it would have come up again somewhere. Right? So 2 is a leaf. And simply, if you algorithmically, it is just that you remove this and then you ask, you remove it and then you ask the least number. Wait, once again. Yeah, you just ask the least number that is not in this list. The least number that is not in this list, apart from what you have already removed, like 4. I've removed 4. The 4 doesn't exist anymore. But in this new list, the least number in the new list, because if you're writing it in a computer, the computer is not so smart, doesn't understand conceptually what's going on. If you tell the computer something in a very straightforward way, so just say, okay, what you do is don't think about all that, just remove the first element of the list and now ask, and also remove the 4 from your original array or something, and then just ask what is the least number not in this. Simple, right? So that's 2, but also we can intuitively understand that it should be 2. Okay, so I'll just draw 2. So you see, this is the reverse is, so it's very important to do the front way, more examples of the front way. Just take some draw trees on your own and just do it, and do it yourself. Just takes time, doesn't matter. Do it. And then this is a very interesting bijection method. Okay, this coding method is a very interesting way to count things. And like this, and then what's next? Let's just quickly do this. So yeah, you see now 2 1 minute. Yeah, now 2 is not a part of our tree. That's how we were writing the code. 1 is the, yeah, so let's, yeah, that's right, but that's right. So 1 is now the parent of something, because now we come to 1. So 1 minute, let me just do it systematically. So this thing, yeah, that's right. So 1 is the parent of something. And what is that something? That something is the smallest thing that is not in this list. And that is 3. And we cannot say 2 because 2 is not a part of our tree anymore. Okay, or just make the 1, and then just ask yourself, okay, I have 1, and 1 was the parent of something. What are my options? my options are that one will be the parent of some leaf, because that's what I'm going to do. What can be the possible leaves? 4 cannot be a leaf. 4 is already out of the picture. 2 is out of the picture. 5 is not a leaf. 3 is the only option. You'll just get the answer yourself. Just ask the questions. Simple, right? In this way, you can continue to make the tree. Okay, let's complete it. So 1 is gone. Now 5. Obviously, 5 is the parent of 1. Okay, that's very, wait, so if I put 5, 5 is the parent. Yeah, 5 is the parent of 1, right? Oh, sorry, I messed up the colors. This and this is black. Okay, like this. And then what should be the last thing? Once again, 5 is a parent of something. What is that something? What is 5 a parent of? What does the last thing suggest? The last thing suggests that 5 is a parent of something. It's a parent of what? You have two options, right? You have 6 as an option, you have 7 as an option. Now think, if I was executing the algorithm, 6 is a leaf, 7 is a leaf, I would have picked the smallest leaves. I would have picked up 6. Very simple. So I think what I did wrong, what I did not wrong, but I should have you just write all the 7 points, 7 dots in front of you. Then you will not go wrong. Or you just do it a few times, you'll, yeah. But you can understand this is a very interesting, and obviously 6 and 7 were joined in the end, right? That's very obvious. The last two, which no, you just join them by default. It's a tree. Well, you get a path. That's a different thing. It's a path basically from 4, 2, 3, 1, 5, 6, 7, but it's a tree. Okay. Very powerful. And then you just apply now just do it yourself. Okay. I'm going to stop the class today. I usually take 60 minutes classes. It gets late for me also. Yeah. This thing, just try to make the list from here and you will see that you get the same list back. That is important because, well, that's how we made the tree basically. Yeah, we didn't really invent a new rule. It's just a reverse of the rule. Okay, just try this for many other samples. Okay, the next time the plan, let me just say, maybe the next time we will do special other versions of this for other kinds of graphs and so on. Okay, and we will investigate this list maybe more carefully. And actually, I wanted to do a few questions, Olympiad type questions. I think next time we will start with them, and then we will come to the list thing. Okay, so yeah, that's what we will do. And yes, so that's it for today. Okay, thank you. Are there any questions about this method? Anything? Please say. I mean, obviously, will be there for you guys to watch and review. I suggest you do that if you get stuck, but you should do the thing yourself also. But yeah, it will be there for you to watch. But if there are any questions, I'll let me know. 5 is not becoming a leaf because 5 appears again here. Right? 5 is there twice, right? So 5, for 5 is a parent. This means that 5 is a parent of something, and then after you have that something, and you do 5 is again a parent of something. So, yeah. Yeah, 6 was. That's right. Yeah, yeah. 6 was the least, right? This was a situation. So, yeah. Okay. That's right. Yeah, it's easy. Yes, and so you would have removed the 6. Oh, yeah, that's right. So your question is correct. So basically, you see, there is a question about whether to join 6 and 7. Yes, yeah. So that's where I'm slightly wrong. That's right. No, that's the right point. 5 is the parent of 6 is correct. Nobody pointed that out. I mean, yeah, so that's right. 5 is the parent of 6 is clear. But why should 6 and 7 be joined is not clear. Right? Why should 6 and 7 be joined is not clear. Because if you are going to execute this algorithm, then that's a minor point, but yeah, one has to make that clear. Yeah, whether 6 and 7 should be joined. So you're saying that we should join 5 and 7? Yeah, that looks, yeah, because if you run the algorithm, let's just run, if you run the algorithm on this, okay, then you get 5. No, but then there is a 1 minute. So then, yeah, no, you're right. 5 and 7 is what should be joined. Yeah. So basically, you can keep it as a rule, maybe. So the last thing you join, I mean, the last thing that's remaining, just join it to the last parent that is remaining. Yes, and that is consistent, right? Because if, for example, this guy has 2 neighbors, then it appears 1 in the sequence. This guy has 2 neighbors, it appears 1 in the sequence. 3 appears only once. So 5 has 3 neighbors, so it should appear, it appears twice in the sequence. Yeah, that is consistent with that as well. Yeah. What was the other reasoning someone was giving? I think that was better. So can you just tell me? I mean, we have explained this already, but can you just again say why we should not join 6 and 7? Someone was saying, said a good reason, I think. It's becoming a leaf. Absolutely, that's right. It's becoming a leaf. That's right. So you should, yeah. So the thing is that the last thing that you're left with, for which nothing is assigned to, just join it to the last parent. Yes, right. So that otherwise 5 would become a leaf at that stage, but it should not. Yeah. So that was right. Okay. So I think that's a good point. Okay, then that's it for today. Thank you for being here.